Right, I'm Elizabeth. I guess this is on, right? Okay, here we go. I'm advised by Ben and Heather. We've been working together on a project for language-agnostic resilience engineering with Wasm. So first of all, show of hands. Who has written buggy software? Exactly, correct answer. Also, show of hands, who writes exhaustive tests? I appreciate everybody's honesty because this is extremely difficult. That's why we all kind of laughed about it, especially when trying to enumerate how systems can misbehave. At best, we write these test cases, and hopefully the test cases that we wrote expose at least the most serious bugs in our applications. And this is especially hard in distributed systems because it just blows up the possible space of issues that could happen. So as an example, here we have an application that has been distributed across several different nodes. So for some single transaction, we can see that node A depends on B, C, and D. So how many possible faults can happen here? We can have a fault with communication at node B, or at C, or D, or any combination of faults on these three different dependencies of A. So this makes 7 different total faulty combinations of communication scenarios just for this single transaction on A. Plus, if we think about the different ways that each of these communications could fault, so maybe there are 10 different HTTP error codes that could be responded on each communication operation, that's 70 total different scenarios this transaction alone could be tested. So that's a lot of scenarios. And so enter resilience engineering. Our systems are guaranteed to encounter surprises, such as faulty communication, and we need to build a system that is able to handle such circumstances gracefully. So all of these scenarios would be really difficult for a developer to enumerate on their own. Obviously, 70 different possible things that could happen. So based on the fact that everyone here admitted to writing buggy software but not exhaustive tests, we know that we're going to have buggy software in our production environment. So how do you actually expose these different types of bugs? When doing local testing, you can create fault scenarios by injecting them somehow, usually at source code level with mocking. And this is the safest testing method since it's easy to tear down, deploy a fresh fix. You also have a lot of observability through debugging, plus it's the cheapest to fix in your local testing environment. And if you have the resources to have a test system, maybe some data center or cloud resources, you could force the system to fault in some scenario. You could force the system to have some faulty scenario in that environment. And you do still have some decent options for observability here. And if you're running in a test system, then you're actually distributed, so you have some more complexity that you wouldn't have had in your local testing environment. You could also do some simulated load, so you have more added complexity there. But this environment still isn't quite as safe as your local testing environment because your bug that you expose could cost some man hours to fix if it's your actual hardware resources and not just cloud resources you can tear down and spin back up. So you could have some type of catastrophic failure that causes time to fix. Plus, it's still more expensive than your local testing environment. And the other option is to force the production system into some fault scenario, observe the behavior there. And there are actually a lot of tools for forcing these scenarios on deployments. But for obvious reasons, this is really unsafe. If your big bug that you expose causes issues with your users, or maybe the bug causes a lot of resource time to go and fix the environment that you've messed up, it just is a lot more expensive in that area. And the testing tools that we currently have for this, you still have to manually configure these test scenarios that you've identified and enumerated. And so it's still the developer still has the load of enumerating your test cases. And it's also very expensive to find bugs at this stage. So the earlier you find a bug, the cheaper and easier it is to fix. So why don't we have better local testing tools for this? Bugs can either be exposed intentionally, under close observation in a safe context through lots of local testing, or bugs can become exposed in production when they're least expected. And let's be honest, they'll probably happen in the middle of the night when people should be sleeping in their bed. But now they're having to respond to some fire on their production system. Let's face it, exhaustively testing our software is really difficult. And bugs exist, hardware breaks, and software fails. So we need to have resilient software that can protect itself against it. And if you're feeling a deep, aching sense of dread for writing all of these tests, I'm right there with you. We need a tool to help us enumerate all the ways the communication can error and generate corresponding test cases for local testing. And we may not be able to be truly exhaustive in how we enumerate all the ways a system can misbehave, but we can try to move the needle a little bit closer to that goal and take the burden of test enumeration off of developers and place it on a tool that can iterate over those possible faults and run the test scenarios for you. And this idea is largely inspired by Chris Micklejohn's filibuster research, which automatically generates test scenarios for fault injection on communication between microservices and Java. And he's done really amazing work in this area, but since his tool is tied to microservices and Java specifically, it can only run in that context. But services in a distributed system could be written in a lot of different languages. And in this context, we can still do some tool-driven inter-service fault enumeration, but the methodology of injection would have to be language-specific. So we have to write one injection tool for Rust, one for Python, and so on for each language and some distributed system do the testing. Or we could do some magic and transform our application and target a lower level language than Rust and Python that a lot of other languages can compile to, like Wasm. So if we target Wasm, we can automatically instrument communication between services to inject faults on them without having to write one tool per language. The methodology of injection will be architecture and platform dependent, but we can theoretically do some specialization and one tool that enables high configurability. This approach would also generalize to allow extensions for other types of faults that aren't just this inter-service communication fault that we're focusing on for resilience engineering. And at a baseline, this tool will just be doing some bytecode level instrumentation that can do anything. You just have to write the code for what you want it to actually do. Plus, as we've talked a bunch in the last several days, Wasm is starting to be used for a lot of different purposes outside of the web. And it's being used in a lot of contexts for running distributed applications specifically. Companies like Fastly and Dfinity are doing this. So while in the previous example, we operated on some transformed version of the production environment and what it looks like, we could, in this specific space, target the actual production language and theoretically run it on the same production engine in order to do this testing, which is really powerful. And this all sounds really great for our tool, but figuring out how to actually architect it without having a tangible and specific context would make things difficult if we're trying to be really generic and don't have a specific platform to kind of think through these problems on. So we're collaborating with Dfinity for this project to give us this kind of first scenario and platform to try this out on. And it's great because we get to work with an actual platform context with literal requirements and constraints. And they're providing this first tangible context. And for Dfinity, the services that you can think of for microservices are actually called canisters. So anytime that I say canister, think of a node or a service in the context of the distributed application. So yeah, what would we do to accomplish this goal of enumerating faults and trying to inject them? Yeah. So we're working at the Wasm level. We need to figure out how to do the instrumentation of Wasm bytecode that performs this inner canister communication. If we can instrument this logic, then we can inject our faults into the scenario, into our communication. And what I mean by this verb instrument is to inject some code into a program's execution that does some operation, in this case, inject faults. And this term is pretty fluffy. So how do you like literally at the bytecode level do instrumentation? And there are a lot of different approaches, as you probably know. And a lot of the approaches have different pros and cons. So we have intrusive approaches, which alter program behavior in an observable way, and non-intrusive approaches that alter program behavior, but not in an observable way, because it runs outside of the application space. So I would categorize both bytecode rewriting and recompilation as intrusive approaches because they directly inject instrumentation code into the application code. So this means their instrumentation code runs in the same state space as the application, which can be very dangerous if the method of injection is not done with great care. I'm not saying that intrusive approaches are inherently creating intrusive instrumentation. You just have to be really, really careful about how you do it to make sure that you're not manipulating your program behavior in a way that you don't want it to. The non-intrusive approaches are a lot safer. You don't have to think as hard about making sure that you're not going to mess up the program's behavior, since it runs outside of the state space of the program. You may be wondering why you would ever use intrusive approaches, but unfortunately, it's sometimes the only option to do that. Emulation and direct engine support require the execution platform to have instrumentation capabilities baked into the runtime. And sometimes your application is locked into running on some specific engine, or maybe you want to observe your program behavior in the actual engine that you run in production. And in these cases, you would only be able to use intrusive approaches for instrumentation like bytecode rewriting. And I'm not going to go into a ton of depth here. The main takeaway is that approaches that are inherently non-intrusive should be preferred, but it's not always feasible to actually use them. Currently, the only Wasm engine with direct instrumentation support, the preferred non-intrusive approach, is Wizard. The way developers must express instrumentation is really clean and intuitive. Also, the engine does some really creative optimizations to make the application run quickly when it's instrumented by leveraging the JIT. Wizard has developers express their instrumentation in terms of probes and logic. And you might notice this is similar to the D-trace structure of expressing instrumentation, if you're familiar with that. So when you are expressing your instrumentation, developers create probes that are tied to some corresponding logic, and then you specify the bytecodes that each probe should attach to an application. So from an expression perspective, it's really high level and generic. It can do anything you want. You literally are just attaching some extra logic to execute when some Wasm bytecode in your application is hit. So we can leverage this expression for manipulating application execution. So you inject these faults when some Wasm bytecode is hit. So how would we express injecting an asynchronous fault on some inner canister call on Dfinity's IC, or Internet Computer, in terms of probes and logic? There are several options on this platform to how to inject a fault. We found that the most straightforward approach to do this would be to actually redirect the original called downstream canister to some alternate fault injecting canister that will return some error response variant that may trigger some failure in your calling canister. So maybe it returns malformatted data, or it can return some error response variant. And this method enables us to still use the IC API for inner canister communication as provided. You're just redirecting to some other target. So how do we actually do this redirection in terms of probes and logic? As you can see from this picture, requests are hitting B no matter what. We need some alternate logic here to do our redirection. So first, we need to define some probes. So let's say that we want to inject a fault when we know that canister A is setting up to call canister B. The IC's API function, the IC API's function that does this is call new. That's the name of the function. So we're going to place probes on all the Wasm calls to the call new function. So you can see here that little pink circle pen thing is representing a probe. So now we have probes on all calls to call new. Now we can just check if the target canister is in fact B. And if it is, then you can redirect the communication to our fault injector canister, which is going to return some fault back to A. And then you can observe the behavior that handles this fault. So now we have a high level picture of what's happening. Let's take a look at what this looks like at the bytecode level. So here is our bytecode that we want to instrument. First, let's place our call new probes. So we have a little probe on there. Now we've attached our probe, which effectively instruments the application. When the engine actually runs my application, it will execute each bytecode and then gets the bytecode shown here with a probe on it. And the engine will notice that the probe is there and execute the logic that's been tied to it. So here, the engine has noticed that this probe is there, and it's going to enter the probe attached logic on the call new call. Then within the engine itself, not in the same state space as the application, the logic attached to that probe is going to be executed, which in this case redirects the call to the fault injector canister. So for readability, this is pseudocode rather than Wasm bytecode. We've called our probe logic and passed all of the original function arguments we passed to the call new call originally. And we passed the original arguments to the predicate check to see if we're in fact targeting canister B. And this function returns a Boolean for whether we want to actually inject a fault in the call, if it is in fact targeting canister B. If it is, then we direct the communication to actually hit our fault injector canister, which will return some fault based on that canister's implementation. So probably some enumerated fault that we had for all the fault scenarios that we enumerated initially. And if it's not targeting the canister and point of interest, then we just perform the original logic like normal. So you call new with the original program arguments. So remember that the fault injector canister would be creating some fault scenario. And after it returns a fault on the call, we can observe the application behavior that will then do something in response to try to handle it. And you can see this is pretty easy to express, really clean. And expressing the fault injecting tool in each test case scenario is also simple, since it's done in terms of interfacing with the engine API rather than doing any direct bytecode manipulation, as with bytecode rewriting. So cool, we're done, right? The problem of instrumenting these applications has been solved. Maybe, maybe not, probably not. Unfortunately, it would be naive if we were to say, okay, we're done at this point. Things just aren't that simple in the real world when we're working with actual systems. So remember, we're collaborating with Dfinity to try to get our fault injection instrumentation working with real code. And doing so has brought to light a lot of properties of real platforms and environments that must be considered when creating what would hopefully be one fault injecting tool to rule them all. And this complicates a lot about our implementation, but it also makes things really interesting, which is what research is all about. So, and everything we showed so far with the probes and logic and all this stuff has been just theoretical for instrumenting IC canisters. So IC applications must use the API provided as host functions to do many different operations such as communication. So when thinking through how to instrument these applications, we're locked into running canisters on Wasm time specifically, and Wasm time doesn't have the direct instrumentation support. So we can't use the preferred non-intrusive approach for instrumenting these applications. So rather than our instrumentation living inside the engine itself, we have to directly inject it into the application's bytecode through bytecode rewriting. And remember, it's a lot more challenging to do non-intrusive and logic injection into an application with this approach, since it mixes instrumentation code and with application code in the same execution space. Another option here would be to port the IC API to run an engine that does have instrumentation capabilities, but that just requires a ton of effort. I'm not going to dig into why. But yeah, so this has to be the new format for how to instrument Dfinity canisters. And even with this constraint, we have already successfully injected a fault using the bytecode rewriting approach. In terms of probes and logic, we directly insert our logic to execute at some probed bytecode by replacing the original bytecode with some wrapper function. And the wrapper function contains the added logic that will then execute when the Wasm bytecode is hit by jumping to that new function call. So here's a more concrete example. Our probed call new call would be replaced with this call to call new wrapper, where the logic for the predicate check and the redirection to the fault injector canister was going to live. So here's the Wasm bytecode, if you're interested. It logically does the exact same thing as the pseudocode I showed you previously. So now we've instrumented our canister directly in its bytecode. We would take this Wasm module, deploy it, and observe its behavior and its responses to the fault scenarios that we've injected. So, okay, let's take a step back. I've shown you that you can use either of these two approaches to inject faults in application at the same high-level expression through probes and logic. And we've successfully gotten bytecode rewriting to work for the Dfinity use case. But remember, there are trade-offs between these two different approaches. So sure, we could stick with the bytecode rewriting method, but do we really want to lock our tool into injecting faults intrusively and with this like harder mechanism? Because that's what would enable our tool to run anywhere and support context similar to Dfinity. Or should we implement this tool that we want to do using the ideal non-intrusive technique of leveraging the engine's direct instrumentation support, but lock ourselves into only being able to support specific systems that can easily port to different Wasm engines? It's a hard decision here, but we do have an idea to try to mitigate these issues. It would be really nice if we had a DSL that enabled us to express our fault injection instrumentation tool at a layer above the actual method of code injection. This would let us implement a single tool without pigeonholing users into the pros and cons of the underlying injection approach. They can use whatever approach makes the most sense for their context and their specific needs. And we can just use our tool to generate the fault scenarios test, translate this into terms of probes and logic written in our DSL, and then iterate over these test cases to run our application. And there's already been a lot of research in creating DSLs for instrumentation, but none that I know of that explores expressing instrumentation that can swap out the low-level method of injection based on user preference. And we hope to pursue this idea in the near future. So what are we planning next to get to this ultimate goal? First, we need to take a step back and layer out the instrumentation abstractions. So split our code into logical units that all work together to ultimately do this fault injection. And then once we have this well-layered structure, we can create the DSL that lives at an abstraction above it. And this would enable us to define the instrumentation without tying directly to the low-level injection approach, and then implement the tool using this DSL that we've created. And then once we have all of that, we would need to have a way to automatically enumerate these fault scenarios that can occur during some communication between services in the system. And of course, there needs to be some type of reporting mechanism to let developers know what issues happen when I ran these test cases. And then since we're expressing this DSL, we need to make sure that it actually works. So we need to get the IC API to support running on top of one of Wizard's interfaces in order to test the alternate injection strategy to make sure that it's still good. And all of these tasks have really interesting opportunities for research and language design, instrumentation optimizations, automatic code generation, human-computer interaction, all those different things, and all of it centered around Wasm, which is pretty cool. So yeah, with that, that's my project we're working on. I don't know if we have time for questions or not, but okay, cool.
Questions for Elizabeth? I think this is very cool and something that working for a company that uses WebAssembly in a cloud environment, and where we're very interested in exactly kind of orchestration scenario. This is something with these capabilities is sorely needed, I think. And I'm also very excited by the intent to have kind of a generalized solution that can be implemented in different ways. My question would be, are you planning to also have the instrumentation, so the engine implementation in other engines besides Wizard? Because obviously that would be, for the Dfinity use case, also be an alternative. Adding that instrumentation approach to Wasm time would be an alternative.
That's kind of an interesting question too, because that's kind of going back to this layering as well. Like laying out the instrumentation, there would need to be a layer that does the interaction with whatever instrumentation API capability of the engine is. So with that layering, if there were to be added instrumentation support for Wasm time, we could create like a layer that could be swapped out for the interaction with Wasm time's API or whatever they did for instrumentation.
And to be clear, I'm obviously, yes, I have a strong interest in the Wasm time side, but to me, it does seem interesting to have something where it's kind of straightforward for engine implementers to say, okay, here is how we can do the host fault injection or in general instrumentation approach, and then engines like Wasero or Whammer or whatever else could use that same approach, while at the same time content producers could decide to do the content rewriting and instrumentation. So
yeah, it would be awesome if more engines had instrumentation support. Yeah. For sure.
So we'd definitely be interested in seeing whether collaboration would make sense there.
There's a question on the chat, Thomas. Yeah.
Oh, yeah.
Have you thought about fault injection on the shop floor? So if you think about a reliable distributed system at shop floor, like from Control X, they presented it. Would you think that would make sense and would be possible to do that in that regard?
Did you say on the control flow? We're having a hard time.
Yeah,
Oh.
you're talking about a resilient distributed system, right?
Mhm.
And we know of the Silverline framework that Bosch Control X or the Wasm from Emily Ruppel was presented, and they're also talking about a distributed system in that regard, and finding bugs in software when the software is deployed in the shop floor, then hardware will crash or humans may come to harm whatsoever. So there's a high interest in bug hunting and then getting rid of those bugs. And fault injection could be a quite viable approach to do that and to test it against maybe a simulation of the hardware to be controlled. And now the question is, do you think that these approaches are also viable to be used for shop floor use cases?
I mean, I would think it would be extendable to do that, because at a low level, it's just probes, logic, and once you hit whatever is of interest for your context in your Wasm bytecode, you can do some type of any logic you want. And so for that specific domain, you would have to do some type of like looking into what your Wasm bytecode of interest would be to be able to define the behavior of your fault injection instrumentation, like what that would need to look like. But from the abstract idea of different things need to happen with these specific entities, like it would be pretty similar, I would think, at a high level, but the low level details of that would be domain specific, which would kind of go back to the layering as well. Like one of the layers would need to be really domain specific knowledge about the actual viable methodology of injecting faults and what that would look like in your domain. So
yeah, I'm also thinking about the Chaos Monkey kind of things, right?
Yeah, because with Chaos Monkey, that's one thing that I was kind of alluding to with software that exists to do this. So with Chaos Monkey, it still is up to the developer to actually enumerate all these faults and then express them in Chaos Monkey to say, hey, I want you to do this to my system. And then it unleashes the Chaos Monkey on your system. But kind of an idea behind this is trying to automatically enumerate those so the developers don't have to do that themselves.
Thanks.
Yeah.
I was going to respond to it.
Oh, yeah.
Yeah, so part of the play with Wizard is to demonstrate the instrumentation capabilities and hopefully standardize them so that eventually all the engines will be able to do the probe thing, and there'll be APIs for that. So we're kind of like on the leading edge of this, and like tactically speaking, you know, working with Dfinity to get to a certain goal of being able to inject faults on their system. It's a lot of work to try to make it run on Wizard. That maybe is a stretch, but the instrumentation capabilities I think should apply to all engines. Yeah, I think we should be able to achieve that goal.
Yeah, and this is just one specific use of it. Like, it's interesting because in Wizard, there are a lot of, they're called monitors. That's, you express probes and logic to create monitors to like observe something about your application behavior while it's running. But this is kind of interesting because the term monitor doesn't really map to this. What we're doing is manipulating rather than monitoring our program. And so this really extends to any type of whatever you want to do in response to something happening in your application as it's running.